Let's start with the core phenomenon behind electromagnetic induction, magnetic flux. Imagine a magnet moving in and out of a coil of wire. As the magnet moves, the amount of magnetic field passing through the coil changes. This change is what we call magnetic flux, represented by the symbol phi. The formula for magnetic flux is phi equals b times a times the cosine of theta, where b is the magnetic field strength, a is the area, and theta is the angle between the field and the area. Now Faraday's law tells us that when this flux changes, an electric current is induced in the coil. The faster the change, the greater the induced voltage. This is the foundation of how generators and transformers work. Lenz's law adds that the induced current always opposes the change in flux, which is why the negative sign appears in Faraday's equation. This opposition is nature's way of conserving energy. Now let's look at transformers, the devices that make long-distance power transmission possible. A transformer consists of a laminated iron core with two coils, the primary and the secondary. When alternating current flows through the primary coil, it creates a changing magnetic field. This field is channeled through the iron core, linking both coils. The changing magnetic flux in the core induces a voltage in the secondary coil, thanks to Faraday's law. The ratio of turns between the primary and secondary coils determines whether the transformer steps voltage up or down. If you connect a transformer to direct current, however, nothing happens. No changing flux means no induced voltage. This is why transformers only work with AC. Let's dive into the math that governs transformers. The voltage induced in each coil depends on the number of turns and the rate of change of magnetic flux. For the primary coil, the voltage equals negative the number of turns times the rate of change of flux. The same applies to the secondary coil. If we assume no energy is lost, the ratio of secondary to primary voltage equals the ratio of turns in the coils. Power is conserved, so the input power equals the output power, meaning the product of current and voltage is the same on both sides. This relationship is crucial for designing efficient transformers and understanding how they scale voltage and current in power systems. Transformers come in two main types, step-up and step-down. Step-up transformers increase voltage for efficient transmission, while step-down transformers reduce voltage for safe use in homes and businesses. However, real transformers are not perfect. They suffer from energy losses due to joule heating in the wires, eddy currents in the core, hysteresis losses, and flux leakage. Engineers use thicker wires, laminated cores, and special materials to minimize these losses. Understanding these inefficiencies is key to improving transformer performance and reducing wasted energy in power grids. Finally, let's see how transformers impact real-world power grids. Efficiency is calculated as the ratio of output to input power, expressed as a percentage. In long-distance transmission, power loss mainly comes from resistance in the cables, which is proportional to the square of the current. By stepping up the voltage, transformers allow us to transmit the same power with much lower current, drastically reducing losses. This principle is why high-voltage transmission lines are used worldwide. Understanding transformer efficiency and grid losses is essential for building reliable and sustainable energy systems.